Well, thanks very much, Matt, for the kind introduction and for the opportunity to extend my streak to 5 Q2B meetings in a row. The 40 years later in my title refers to Richard Feynman's famous talk at a conference in 1981, which, as Matt reminded us, was published the following year, in which he proposed that quantum computers would be able to solve problems beyond the reach of conventional digital computers. The 4 years later refers to the 4 years since the first of the annual Q2B meetings in 2017. Actually, this picture of Feynman is from 1984, and the picture of Matt Johnson is from 2019, but I wanted to show them gesticulating at one another across the intervening decades. One thing that's changed in 4 years is that in addition to being a professor of theoretical physics at Caltech, I now have an affiliation with the company. I'm an Amazon scholar involved in the Center for Quantum Computing that Amazon Web Services has launched at the Caltech campus. But as in the past, I'm speaking here not as a representative of any company, but as someone who's been doing research in quantum information science for over 25 years. Quantum Computing 40 years later is also the title of an appendix I contributed to a second edition of the Feynman Lectures on Computation, which will be published soon. I was invited to provide some perspective on how the topic of quantum computing has advanced since Feynman discussed it in the 1980s, and you can find that article on the archive. Looking back, we can appreciate that Feynman's talk in 1981 really was a watershed. He articulated clearly that there are problems, in particular those involving properties of quantum systems, that we don't expect to be able to solve efficiently using conventional digital computing technology. But with quantum computers, we would be able to eventually solve those problems. Now, I wasn't very impressed by this idea back in the 1980s, even though, as Matt said, Feynman and I were colleagues, and we often talked about science, but never about quantum computing. But Feynman foresaw that we should eventually be able to build and operate these quantum computers. And fortunately, there was a small community of people who appreciated Feynman's vision, among them David Deutsch, Richard Jozsa, Umesh Vazirani, and others, and they pushed the subject forward. What grabbed my attention, and that of many others, was Shor's factoring algorithm. That was 27 years ago. But Shor drove home that even beyond the arena of quantum physics, quantum computers could have surprising power compared to their classical counterparts. And I became entranced by the idea that arcane principles of quantum physics would enable us to solve problems that couldn't otherwise be solved. And thinking about that eventually led me to change the direction of my own research from elementary particle physics to quantum information science. Now, 4 years ago, I was unable to resist Matt Johnson's persuasiveness and sincerity when he invited me to speak at Q2B, and I thought a lot about what to say. So during the Christmas break after the talk, I wrote up a version of it to post on the archive. And then a few months later, Jake Taylor, who was at the White House in those days, suggested maybe it should be published, which somehow hadn't occurred to me. And so it appeared in Quantum. And I want to revisit some of the things that I said in 2017 in the light of developments since then. The main message I had in 2017, which I would continue to promulgate today, if it's condensed to 2 sentences, is this: that there are 2 central questions that the field of quantum computing faces. How are we going to scale up to quantum computing systems that are large enough to solve really hard problems? And once we have that power, what will be the most effective ways of using it for applications to both science and industry? I think these are both wide open questions today. And that realization should provide guidance for how we focus our effort now. So for example, one can ask, what should we be doing with the noisy intermediate scale quantum computers that we have now? And two obvious answers are, we should use them to learn how to build more powerful quantum computers and to learn or provide some clarity about how those more powerful quantum computers could be used to advance science and for commercial applications. I'm actually fairly excited about what can happen in the next 5 years. I think we can expect to see notable progress toward fault-tolerant quantum computing, quantum error correction, and I'm anticipating that there will be scientific discoveries enabled by the programmable simulators and the circuit-based quantum computers that we have now and will be developing in the next few years. One of the things I said in 2017 was this: as the quantum community eagerly seizes the impending opportunity to experiment with NISQ devices, we must not lose sight of the essential longer-term goal, hastening the onset of the fault-tolerant era. We want to make quantum error correction happen. What are the capabilities that we need? Well, we'd like to be able to do many repeated rounds of error syndrome measurement for quantum error correction, and to see that as we increase the size of the code, the number of physical qubits in a code block, we can make quantum memory times improve rapidly. Now, the ion trappers might protest that they don't care so much about quantum memory because their atomic qubits are already very long-lived, and that's true. But all of the currently pursued platforms and those we foresee in the near future face the same challenge. If we want to run powerful algorithms, then we're going to have to do entangling 2-qubit gates with much lower error rates than we can achieve today. So we would like to see that we can do 2-qubit gates at the logical level on protected qubits with improved error rates compared to those on the physical gates. And we'd like to validate that as code sizes increase, those logical gate fidelities continue to get better and better. And that hasn't been achieved yet. But there have been encouraging developments in the past year in quantum error correction, of which I'd like to highlight two. One from Google, one from Honeywell. The Google group studied the quantum repetition code using 21 qubits in the Sycamore processor, codes up to length 11 with 10 ancilla qubits used to measure syndromes. Now, importantly, this is not a full-fledged quantum error correcting code. It can protect against dephasing errors, but not against bit flips. But still, one can do an impressive demonstration. They were able to do up to 50 repeated rounds of syndrome measurement, each taking about a microsecond, where most of that time is used to reset the ancillas to prepare for the next round of syndrome measurement. And they were able to see that the logical error rates due to dephasing do improve sharply as the code size increases by about a factor of 10 when the code distance increases by 4 from 3 to 7 and from 7 to 11. The Honeywell demonstration really was a genuine quantum error correcting code, a 7-qubit code, which can protect against an arbitrary error acting on one of the 7 qubits. And they too were able to do repeated rounds of syndrome measurement, each taking about 200 milliseconds. So notice the difference in cycle time between the superconducting and ion processors. That's something we'll bear in mind as in the future it becomes increasingly important to know what is the time on the wall clock to execute a quantum algorithm. In the Honeywell architecture, they move ions into processing zones where they can do high fidelity entangling 2-qubit gates. They can do several such gates in parallel. And after movement, they cool the motional states of the ions using sympathetic cooling with another species of ion. And it's that cooling that enables them to do the repeated rounds of error correction. But at this stage, there isn't any platform in which the error rates for 2-qubit CNOT gates are low enough so that by using coding, we can improve the gate fidelities. So where do we think we're going to go? The best idea we have for improving quantum computing error rates through coding is the idea that's been around for 20-some years to do a type of topological quantum error correction by means of the surface code, as Kitaev suggested. The surface code has two big virtues. In order to extract error syndromes, it suffices to do geometrically local processing in a two-dimensional layout. And furthermore, to extract each bit of the syndrome involves a quite simple quantum computation acting on only 4 of the qubits in the code block. The surface code can tolerate higher error rates because of these properties than other codes that we're likely to be able to use in the near term. But the overhead cost of quantum error correction using the surface code and the number of qubits that we need and the number of gates is substantial. So let's say that we could do CNOT gates with an error rate per gate of 10 to the minus 3, which is better than has currently been done in multi-qubit devices. And let's say we want to run algorithms for which we're fairly confident there would be quantum advantage. That's likely to involve hundreds of qubits and millions of gates. So to get the required logical error rates to run such an algorithm, we'll probably need a few hundred physical qubits for each logical qubit and tens of thousands of qubits altogether. And to run a more ambitious algorithm, like breaking a public key crypto system with Shor's algorithm for that error rate of 10 to the minus 3 for the physical gates, it's estimated that we would need 20 million physical qubits. As the gate error rates improve, the overhead cost goes down, but it's still going to be substantial, even with a CNOT error rate of 10 to the minus 4, to run algorithms that we know, which we think will show quantum advantage. We may still need hundreds of physical qubits for each logical qubit. And those numbers are daunting from the perspective of the current status of the technology. So we have some big challenges. Something I said on a more upbeat note in 2017 was this: physicists are excited about NIST technology. It gives us new tools for exploring the physics of many entangled particles. And here too, there have been exciting developments in the past year, of which I'll highlight 2. The Harvard-MIT group, using 219 Rydberg atoms, recently created and confirmed the creation of a new quantum phase of matter called a quantum spin liquid. Theorists have been speculating about quantum spin liquids for nearly 50 years, but there's never been a conclusive experimental observation of this type of phase of matter which has long-range entanglement. And there are 2 main reasons for that. First of all, for the ground state of a quantum material to have the long-range entanglement characteristic of a quantum spin liquid, the material has to have just the right properties. And secondly, to read out the signature of a quantum spin liquid requires a complicated measurement, a collective measurement on many qubits. The Rydberg platform is highly programmable and flexible enough to create the right conditions for a quantum spin liquid to form, and sufficiently controllable so that one can read out the observables to detect that quantum spin liquid behavior. In an experiment suggested by condensed matter physicists at Stanford, Princeton, and other places, the Google processor, using up to 20 qubits, investigated something called a discrete time crystal. That's a periodically driven phase of matter in which the system undergoes persistent oscillations indefinitely at a different frequency than the drive. The idea of a discrete time crystal was first suggested theoretically less than 10 years ago, and there have been previous investigations of the phenomenon. But thanks to the relatively high 2-qubit gate fidelities and the single qubit control, in Sycamore, a more convincing demonstration of discrete time crystals was possible. So note two things here. First of all, 4 years ago, the Rydberg atom platforms were not so much on the radar screen of quantum platforms under development. And now they're advancing rapidly. And that reminds us that quantum hardware is really still in a very early stage, and further surprises are likely to arise in the future. And notice that while the Google experiment was done with a gate-based universal quantum computer, the Harvard-MIT experiment was done with a programmable analog simulator. So that reminds us that both of these approaches are complementary and valuable for investigating properties of phases of matter. You might not care so much about quantum phases of matter, but I submit that you should for two reasons. First of all, of the applications we foresee most clearly for the quantum computers we hope to develop in the future, those that seem most likely to have a broadly felt impact on humanity are the applications to chemistry and materials. And it's exciting to see that with the NIST platforms we have now, we can do investigations of quantum matter that haven't been possible till now. And secondly, it's possible that these investigations will help to ignite new ideas for doing quantum error correction and fault tolerance, from which we'll benefit in the future. I made some comments about quantum machine learning in 2017, including this. Quantum deep learning might be very well suited for quantum tasks, but for applications of deep learning that are widely pursued today, it's unclear why quantum networks would have an advantage. And a few months after I wrote up the talk, Yiwen Tang, who was at that time an undergraduate student working with Scott Aronson, dropped a bomb by showing that some of the proposed approaches to getting exponential advantage in quantum machine learning can be dequantized. That is to say, there are quantum-inspired classical sampling algorithms that can nullify the exponential quantum advantage. And that work by Yiwen initiated a flood of further dequantization results by her and by others. In fact, assessing the implications of dequantization is subtle, because even polynomial speedups could be practically valuable, and because some of the classical algorithms assume access to a classical description of a quantum state that might not be fully realistic. But dequantization has raised questions about the prospects for quantum machine learning, and I think it encourages us to think afresh about the possible ways of using quantum learning applied to quantum problems. And that leads me to some recent work that I was involved in, led by a Caltech student, Robert Huang. What we did is we studied the problem of trying to learn properties of some unknown quantum state or process. So let's suppose that we can do repeated experiments to prepare identical copies of a quantum state that we want to learn about, and contrast two scenarios. In the conventional scenario, we measure the copies of the quantum state one at a time and store the measurement data in a classical memory and then process it with a classical computer to try to estimate the properties of the state. And in a quantum-enhanced scenario, we can deposit multiple copies of the state in a quantum memory and process that quantum data with the quantum computer to try to learn about that a priori unknown quantum state. And what we showed is that, at least for some tasks, we can learn properties using exponentially fewer experiments in the quantum enhanced setting compared to the conventional setting. And furthermore, the quantum processing that we need to do to realize that advantage is actually quite simple. We just need to do entangling measurements across two copies of the state, which makes it feasible to demonstrate the advantage with technology that we have now. In this case, we used up to 40 qubits of the Sycamore processor. So here's some results from one of our experiments. The task is, when we're provided access to copies of the state, there's a learning phase in which we try to learn properties of the state, and after the learning is completed, we're asked to predict the expectation value of some observable, which is chosen from an exponentially long list. And in the quantum enhanced scenario, we can store two copies of the quantum state and perform entangling measurements across the two copies. And some data is shown in the panel on the right. This is the number of experiments we need to do a successful prediction as a function of the system size n, the number of qubits. Because we stored two copies in the quantum enhanced scenario and used 40 qubits, we could go up to a system size of 20. Theoretically, if we had a noiseless device, we could make accurate predictions with a number of experiments that's independent of system size, but we can prove that in the conventional scenario, a number of experiments that grows exponentially with system size would be needed. So from the data, you can see that the number of experiments to make a prediction did rise slowly as a function of system size. That's because of the noise in the device. But at a system size of 20, the number of experiments in the quantum enhanced scenario is already smaller by a factor of a few thousand compared to our lower bound on how many experiments would be needed in the conventional scenario. And in fact, we weren't able to carry out the conventional learning method for system size larger than 8, just because it was too costly in the number of experiments required. So we hope this can be a model for how in the future quantum sensing networks might make use of quantum memory to achieve a substantial advantage. And we hope that it will stimulate people to think more broadly about where to seek quantum advantage in learning problems. So I think we're seeing evidence that we're at the early stages of a new era in quantum science, that we have the capability now to do experiments and investigations of quantum matter that weren't possible before. And we can anticipate that as our technology continues to advance, we'll be able to ask and answer increasingly sophisticated questions about highly entangled states of matter that are more and more complex. So let me sum up. It's likely that to achieve quantum advantage for commercial applications, we'll need quantum error correction. And that's going to take the time, nobody knows exactly how long, to develop. But there are exciting prospects over the next 5 years or so, I think, such as progress towards fault-tolerant quantum computing and unprecedented opportunities to explore exotic properties of quantum matter. So that means we're really at the beginning of fulfilling Feynman's vision of using quantum technology for simulation of complex quantum systems. But we really have enormous challenges to face in order to realize our aspirations, and no doubt we will need many future advances in basic research to meet those challenges. So let me end with this thought. I think we all share great excitement and anticipation for where quantum science and technology can go in the future. And if we're going to achieve great things, we have to stay optimistic about the future. But there's a line between setting ambitious goals and fanning inflated expectations. Some people may draw that line differently than others. But I think for us as a community, in the long run, we'll be better off if we try to stay on the right side of that line. All right, thanks for listening. I think we left some time for questions. Is there, am I supposed to answer questions? Okay. How much do we have? A few minutes, right? Okay. Any questions? Oh, there are people out there. What do you know? Okay. So the question was, can I speculate further about what the implications might be of this recent quantum learning experiment for quantum sensing in the future? Well, what I'm envisioning is that, well, first of all, I don't know, but I think it opens the possibility that, let's say we're trying to detect photons with some kind of distributed multi-sensor network. So what we typically do now is really throwing away a huge amount of information. We detect the photons. And there are phases in the multi-photon state that we're completely blind to. So there's a lot of information we're not taking advantage of. Suppose, though, that we could, as photons arrive, transduce them and deposit them in a quantum memory and do entangled measurements across those photons. So at least in principle, I think this result shows that for some tasks, we can get an exponential advantage that way in the system size, the total number of sensors in the network. What I don't have a very good answer to is, what would be the practical impact of that? What kind of imaging, say, would we be able to do which would otherwise be out of reach? But I am optimistic that we can come up with some impactful applications. I guess I have time for another.
Yeah, this is Tim from Accenture.
Where are you? I don't think I see you.
Yep.
Over there? Oh, yes, thank you for waving.
Of course. Wait. So I think my question goes in a very similar direction. Yeah, but the learning experiment that you showed is, I think, very interesting. And I have a question, if I kind of grasp it correctly. So does it essentially enable us to also think in a more technology direction, to go to, let's say, more complex states, higher intensity, for example, like quantum radars or so?
Well, I'm not sure. So the question was kind of a follow-up to the previous question about the technological ramifications of this advantage in learning.
Yes, exactly. So I mean, if you say you can evaluate now more complex quantum states, does it also enable technologies like quantum radars to go to higher intensities, more complex states?
Yeah, so the question is about quantum radar, but I guess it's also a broader question. So the idea of quantum radar is that we can prepare entangled states and send one member of an entangled pair, say, to a target. When it gets reflected back, then we can do entangled measurements, and that has some theoretical advantages. And in the case of many photon states, it would have a greater advantage. Now, most of the advantages in sensing that people have considered up until now are not exponential advantages. Typically, when we consider quantum sensing networks, we can compare the case where we can have entanglement shared among the nodes in the network with the case where there's a product state shared by the nodes, and can show that there's an advantage which goes like the square root of the number of nodes by making use of entanglement. Turning that into a practical advantage is challenging, but theoretically it's there. And I haven't actually thought specifically about the application of quantum radar, but it's a good suggestion. I think having advantages which are really exponential in the number of sensing nodes rather than a square root of the number, well, obviously it's a big difference. But how to make practical use of that potential advantage is still pretty wide open.